Hello, welcome to another Stat 510 video. In this video, we're going to continue this tradition we're sort of developing here of introducing methods that are extremely generic. So we've seen the empirical distribution, we've seen the plugin principle, we've seen simulation, and now we're going to introduce the bootstrap, which, like these other things, is something that sort of is, um, how do I describe this? It's sort of a method that it kind of always works, meaning that it's super generic, so it can apply in many situations, and it might not give you the best answer, but it gives you something that's roughly decent, and it's easy to apply, and you can just always do it. Somewhere I really wish I remembered where I learned this and who I could acknowledge with this expression, but someone I heard refer to these sorts of methods as rough and ready statistics. So they're always ready to go. They'll get you an answer. It might not be the absolute best, but it's an answer and it'll get it for you, and it kind of, you can depend on it in that way. But this video, we're going to talk about the bootstrap. So to talk about the bootstrap, we're going to need to sort of redevelop the setup that we're in, which is, we have an IID sample from some distribution, and we're interested in estimating some property of that distribution, and the way we do that is with a statistic. And so far we've basically seen that the way to develop that statistic is through the empirical distribution and developing a plugin estimator. Okay, so what we introduced last time is this notion of, well, when we do that, we often want to know the distribution of that statistic. That is, the sampling distribution is what that called. And I also mentioned that, hey, we'd often like to know some follow-up quantities about that distribution. One of them I mentioned was the variance. And if you think about it, if you had the variance, you could probably do something like this and develop a confidence interval. So we'll keep that in mind for a couple minutes from now. Okay. We mentioned that sometimes it's very easy to get a sampling distribution. And we also said sometimes it's not so fun. And we then looked at simulation as a way to sort of sidestep this problem. So simulation provides a way to basically say, well, I don't want to do the math here. I don't want to do the probability. I just want to use compute power to get me an answer that is correct. So we introduced this notion of simulation, which is basically, okay, well, for now, and again, the secrets, well, not the secret sauce of simulation, the assumption of simulation that won't work in practice is that we have to know the distribution. And so then if you know the distribution, well, we simulate data from it, calculate the statistic, repeat that process a bunch of times. It looks something like this, and then use the empirical distribution of those statistics that you generate as sort of an estimate of the true distribution. The true sampling distribution it is. But again, like I just said, the big problem there in practice, we don't know that distribution that we're generating the data from. So for practical applications of data analysis, you're not going to be able to use simulation. Simulation is more for the research side of things. We want to understand properties of our estimators, and we can concoct situations where we know the distribution and then do simulation studies and see how our statistics behave. But in practice, can't do that because the whole point of practice is inferring that F in the first place. So we don't know it, so simulation's out the door. Turns out there's a really, really clever idea that can get around this. Don't simulate from the true distribution. Simulate from the empirical distribution. If you do that, what you have arrived at is something called the bootstrap, which is developed by Bradley Efron. It's a name you'll probably hear a few times in statistics. This slide makes it seem like a really simple thing, and it kind of is, and that's the beauty of it. But it's incredibly useful. Okay, so this slide should look really, really, really similar to the one we had for simulation. So in some ways, the only things that have changed are this f hat here instead of f, and then some notational things. So people often use stars to indicate something that was bootstrapped. So in this generate data step, so the thing that we're generating here, we would call this a bootstrap resample. Okay, so it's called a bootstrap resampling because while I have introduced this idea as sampling from the empirical distribution, it's actually equivalent to the following, which is that if you take a sample of size n from the original data with replacement, that's the same as sampling from the empirical distribution. Uh, say of size n. Okay, so those two ideas are interchangeable, but oftentimes when people are talking about Bootstrap, they call it sort of a resampling based method. Some people call it a simulation based method. Some people call it a resampling based method, but they're both doing the same thing. So essentially, what you're doing is you're picking out data points from the original sample. Is what you're doing until you have n of them, and then you calculate the statistic. That statistic is called a bootstrap replicate. Okay. And then you do that a bunch of times. B. Okay, so then you have a bunch of bootstrap replicates. So sort of faked simulated values of the statistic that we're interested in. So then we can use the empirical distribution of these. As an estimate of the true sampling distribution. Okay. Right, I said these things already. So this diagram should look incredibly familiar. Basically, all we've done is replaced f with f hat. And then a few notational differences, like basically stars, just to indicate that these aren't samples from the original distribution, but samples from the empirical distribution. That is, their bootstrap resamples. So again, this here is the empirical distribution. Okay. And again, this here is a random sample of size n from f hat. And again, this is equivalent to just taking the original data set and picking n random observations from it with replacement. Same thing. Okay, so that makes this thing here a bootstrap resample. So it's essentially a faked version of a sample from the actual f. And then this here is a bootstrap replicate. Which is basically a faked version of a value of the statistic. Okay, cool. Oh, and then, of course, you repeat. But you already knew that. Okay. So I want to focus on now one particular property of the sampling distribution that we might be interested in, which is the variance, which I sort of mentioned earlier could potentially lead to development of a confidence interval. So that is, so I have some statistic that I care about, T of n, and I want to know the variance of that statistic. So to do so, I would need to know the sampling distribution, which often we won't. But so one way we often deal with this is obviously we're not gonna know that variance. So we'd estimate it. So what I've denoted here is if you replace, if you do the expectation with respect to f hat instead of f, well, that's the plugin estimator. Right? So for example, if our statistic was a sample mean, we would estimate that variance by sigma squared hat over n, where this sigma squared is, I'm going to call it the quote unquote sample variance. Because we're doing the plugin method here, it would be sigma squared hat would have a 1 over n, not a 1 over n minus 1. So just note that. Okay. And so in the case of x bar, we could get that. Like, but what we saw last time is like, if the statistic is something more complicated, like itself a variance that is a sample variance, or like a quantile or a median or something like that, even getting that is difficult. So what we can do is this procedure down here. So we obtain this quantity that we call v underscore boot. So this thing here is the sample, quote unquote, variance of the Bootstrap replicates. The notation there is quite annoying, but essentially it's just the, if you have all these t values of the statistics, just take the sample variance of those things. That's what it is. So that would be the Bootstrap estimator of the variance of the statistic. That's a mouthful. I'm going to say it again. So this procedure that we have in this last line here, that is how to estimate the variance of the statistic using the Bootstrap. Okay, cool. And that's useful because sometimes we can't get the plugin estimator because it's just too analytically difficult. Okay, great. So if you take a square root of that quantity, we could call that a standard error. So we could call that the Bootstrap standard error. Well, so we now have an estimate and a standard error. So to me, that sort of screams, make a confidence interval. Confidence oh my gosh. I should stick to writing math, not words. Okay, so that's one of the big uses of the Bootstrap. While it sort of is, you could generically think of it a way to sort of like estimate the sampling distribution. Really, one of its biggest uses is making confidence intervals. And there are many ways to do this. We're going to look at 3. We're not going to go into the derivation of them. We're not going to go into the justification of them. Those are in the book. We're going to, in practice, sort of look at how well they work because we're going to check the coverage of these on the homework. But I'm just going to introduce them here. Okay, so the first one is called the normal Bootstrap confidence interval. And we're making a 1 minus alpha times 100% CI here. So you just simply take your estimate plus or minus your relevant z critical value times that Bootstrap standard error. That's a confidence interval. This is only good if Tn is approximately normally distributed anyway. Okay, so to me, this is not all that exciting, although many statistics do end up being approximately normal, but that's a restriction that to me feels a little bit icky when we're trying to say like, hey, this is a method that works under a bunch of situations. So I don't like having to throw that little clause in there. So let's move on to another one. So there's something called the pivotal Bootstrap interval. So we're switching notations a little bit here, mostly to stick with the book's notation of these things here. So instead of t being the statistic, I'm going to use theta hat as the statistic, which in this case, that's just to make it much more clear that we're trying to estimate theta. Because, with the confidence interval, you're trying to do estimation. So below that, I have theta hat 1 star, theta hat 2 star, and so on and so forth. Those are the bootstrap replicates of theta hat. So the way you make the interval, oh, I should write that. So these are bootstrap replicates of theta hat. Okay. So then the way you can construct a confidence interval is through this expression here, and I have to sort of mention two things here. So this is a 1 minus alpha sample quantile of the bootstrap replicates, and this is an alpha over 2 sample quantile. So essentially, you look at the bootstrap replicates and you use like a quantile function inside of a statistical programming language, and you pull out the alpha over 2 quantile and the 1 minus. Sorry, I need to look something up. I think I'm missing a divided by 2 in these notes, and that's embarrassing. But I'm not confident enough in the moment to correct it, so I'm going to cheat and look it up. Yeah, I should have just been confident. There should be an over 2 right there, and an over 2 right there. And pardon me, I'm going to correct this on the fly. I need to remind myself to post this correction. Okay, sorry about that. Okay, so that's another way to make it, and this will become clearer when I do an example in a second. The last way, which I kind of weirdly, this is simultaneously the least intuitive and the most intuitive to me. But this is like the most generic. So to me, this one makes the most sense. So get the bootstrap replicates of your statistic, and then just take the alpha over 2 quantile of those, the 1 minus alpha over 2 quantile of those, and in between there, that's your interval. This one just makes sense to me for some reason. I think this is one of those things where if you think about it a little bit, it gets it makes a lot of sense. But if you think about it a lot, it might not make a lot of sense. Then you have to think about it a ton more for it to make sense. But for all three of these, justifications and mild derivations are given in the book, so have a look at them. What I want to do is apply them in R real quick to hopefully give you a better idea. And so sort of the idea here is, first you write a function that resamples the data. And then calculates the statistic. Then you replicate, then you calculate your intervals. Okay, so, I should say, I'm saying resamples data here, not sample data from the empirical distribution, because when we actually do this in practice, it is easier to imagine it as sampling from the original data. So let's just do it. Okay. So I'm gonna make up an example on the fly. I need some data. Okay, so what this data is it's physical characteristics of penguins. Okay, so let's I'm not in a more applied class I would do some exploratory data analysis here and talk about the data much more, but I'm just going to focus on this variable, which is the body mass in grams of these penguins. And what I want to do is I'm going to say our statistic of interest is the sample median. And so our parameter of interest is the population median. So what I want to do is I want to make a confidence interval. Here, let's say we want to make a 90% CI for the population median, and we want to do it 3 ways. What we call the normal, pivotal, and what is the last one? Percentile. Okay, cool. All right, and again, I'm just gonna call this mass, because I don't want to have to deal with the data frame structure. I just want to work within a vector. Okay. So this is our data. So we don't know any distributions here. We got to figure it out. All right. So first thing I want to do is note what happens when I do this. So if I use the sample function on the original data, this is a resample. But right now, and by default, when you use the sample function on a data set, it returns a sample of the same size. So we're good there. But there is one problem, which is that these values are just reshuffled these values, because we didn't do the sampling without replacement. So what I need to do is sneak replace is true in there. That's different. Here, the way I'm going to verify to you that it's different every time is I'm going to wrap this in sum and then run it a bunch of times to see how that number's changing. If I set this to false, oops, that number's not changing, because all it's doing is shuffling the observations. It's not generating different data sets. Okay. Okay, so essentially if I keep doing this, each time I do that, that's creating a Bootstrap resample. Okay. So I'll call this a boot sam. Okay. And then I want to calculate the median on that sample. So if I repeatedly run this code, those are generating Bootstrap replicates. So what I should do, sort of following the simulation example, so I'm going to call this boot data calc median. So I'm going to do it like this. So here I'm going to put data. So this is kind of generic. So this will work for anything. And so I'll pass it the data mass. So if I do, so now all I've done is written a function, so just slightly easier to run. So now what I'll do is replicate, 5,000 is generally a good number. So I'm going to call this boot median replicate, something like that. I know that's like a long name, but it's descriptive. It's good, right? Okay, so there are the Bootstrap replicates. Because I'm going to need it, I'm going to write a function that calculates the variance of a vector. So I'm going to do x minus mean x. Square those, oh gosh. Square those things, sum those things, and then divide by the length. So this is just variance with n instead of n minus 1, but that's technically what we need to be using here. Okay, so I'm going to calculate the variance of those things, and I'm going to take a square root of that. So I'm going to call this the se underscore boot. So this is the Bootstrap standard error. Okay. I have everything I need now. Let's do the normal one. Oh, I have one more thing I need to do. The estimate. So this is the non-Bootstrap. This is just the usual plugin estimate of the variance. Median. Okay, so for the normal interval, so I need to do roughly estimate plus or minus critical value times standard error. So the estimate is there, and then we'll do plus -1, comma 1 times Q norm. I think I need to do 0.05, right? Actually, let me check that. Except I'm gonna want this one. Yeah, I want the positive value. Okay, cool. And then times the standard error. There we go. Oh, se boot. Okay, just to be sure. Okay, cool. So there is my interval. So this little trick here is a nice little way to write it in one line without having to do the lower and upper separately. So here we have our lower bound. Here we have our upper bound. Okay, cool. Let's look at the pivotal. Okay, so to do this, I need to do, well, let's refresh our memory real quick. Okay, so it's 2 times the estimate minus, okay, the upper and then the lower. Okay, so I think I can do this. All right, so it's 2 times estimate minus quant. Well, here, let's do this first, actually. It doesn't like that I have that. Okay, quantile. So let's do C 0.05 and 0.95. Except that I need to put the data in there. Okay. Oh, right. Is that right? Okay. Except I had it right previously. Okay. Because I want the subtraction. Yeah. So it should just be exactly this, right? Wait, is that right? Wait. Sorry, the pivotal interval always messes me up. No, that can't be right because they're... Oh, I see why I was getting screwed up. Sorry. We need to look at this quantity closely. Okay, and I need to put 9.5 here and 0.5 here. And the way I'm going to know it's right is if this number needs to be bigger than this number, so it makes the lower bound correct. So, okay, do this, do that. Okay, there's my interval. Okay, so normal interval, pivotal interval, they're similar. Okay, this is probably confusing. Do one yourself. I think you'll do fine. Okay, I probably should have done percentile first. So percentile's pretty simple. It's this, except it would be this order. There's our percentile interval. It's actually the same as the pivotal interval here. Okay, so that was kind of a lot pretty fast, but I want to mention some things. So this was just setting up data. That's not important. Okay, this was getting our code set up, not important. This, super important. So realistically, this step is always going to happen. You resample your data. And then this step, while we calculated a median, whatever statistic you're bootstrapping, you calculate it here on this data. Then you repeat it a large number of times. 5,000 is a good rule of thumb. Then you can calculate the standard error and do a normal interval, or you can do this pivotal or this percentile method. Yeah, so that's it. It's really that simple. Like these are just always going to apply. You just put your statistic here, and it just kind of works. I think what you'll find is you're going to have some questions, and some of them are going to be answered on the homework. Some of them are going to be brought up in the homework, and you want to think about it more. But so one of the things you're going to want to think about is the question, does this work? And then the follow-up question, when does this work? So I think there's a lot of conflicting information floating around about this. And I posted, again, like a bunch of links with some good discussion on this that I think you should start looking at. But ultimately, I think it should be somewhat clear that the thing that's going to make this work is if the sample you had originally is very representative of the distribution that it came from, and it's reasonably large, so large enough that it sort of well represents that distribution. That's a awful heuristic to deal with in practice, but that's kind of the way it is. And you'll sort of investigate that a little bit on the homework. Okay. I believe I've begun rambling, which means I need to stop this. Okay. So, as always, if you made it to the end of the video, good job, and I'll see you in the next one.